Hello everyone, I'm Lu Qi, a graduate student at Beijing Institute of Technology. Today, I'd like to share some of our research on knowledge transfer for few-shot segmentation of novel white matter tracts. White matter tract segmentation based on diffusion MRI provides a quantitative tool for the analysis of the brain characteristics. It identifies specific white matter pathways and brings deeper insights into brain development, function, and disease. For example, tract-specific white matter changes are associated with visual hallucinations and low visual performance in Parkinson's disease, and the observation of them can offer important information about early Parkinson's dementia diagnosis. To achieve automated and accurate white matter tract segmentation, convolutional neural networks or CNNs have been applied to the segmentation task, and they have achieved state-of-the-art performance. For example, CNNs can be used to perform volumetric white matter tract segmentation that directly labels each voxel in a DMRI scan according to the white matter tracts it belongs to, based on fiber orientation maps or diffusion feature maps. It is also possible to label fiber streamlines based on the feature maps. CNN-based methods generally requires a large number of manual delineations of white matter tracts for training. These delineations can be very label-intensive and costly. Although there can be existing delineations of certain white matter tracts that are accumulated throughout time, the expensive delineation can be a particular disadvantage when novel white matter tracts are to be analyzed. The novel white matter tracts mentioned here are those that have not been included in existing manual delineations. It is desirable to perform accurate segmentation of these novel white matter tracts with only a few delineations, and this can be achieved by exploiting the knowledge learned about existing white matter tracts. We're supposed to address this problem. Now let's organize the problem and formulate it. Suppose we have a CNN-based segmentation model trained with abundant annotations for a set of white matter tracts, and the annotations may not be accessible. We are interested in the segmentation of a novel set of white matter tracts that are not considered during the training of the given model. Only a few manual annotations are available for these novel white matter tracts. Our goal is to achieve decent segmentation performance for the novel white matter tracts given the scarce annotations. To achieve such a goal, a common practice is to transfer the knowledge in the model learned for segmenting existing white matter tracts to the segmentation of novel white matter tracts. Suppose the input image is X. We denote the network models for segmenting existing and novel white matter tracts by ME and MN respectively. These two models share the same network structure except for the last task-specific layer. Suppose the task-specific phase in the last layer LEOME and the last layer LNOMN are denoted by theta E and theta N respectively, and the other ways in ME or MN are denoted by theta. From X, we can get a multi-channel feature map F. Then the logits HE or HN for existing or novel white matter tracts is computed from F with LE or LN. Finally, through the sigmoid activation, the segmentation probability map PE or PN can be obtained. Intuitively, the knowledge transfer can be performed with the classic fine-tuning strategy. In the classic fine-tuning, the learned values theta tilde of theta for segmenting existing white matter tracts is used to initialize theta for training MN. And only theta n is randomly initialized. In this way, the knowledge learned for segmenting existing white matter tracts can be transferred to the segmentation of novel white matter tracts. However, it completely discards the information about theta E in the last layer LE learned for existing white matter tracks. The information in this discarded width could also bear information relevant to the segmentation of novel white matter tracks. This possibility allows us to explore the discarded information in LE as well for training MN, because LE and LN generally use a convolution with a kernel size of 1 to classify each voxel, which is equivalent to matrix multiplication plus a Bayes vector at each voxel. We can rewrite the task-specific with theta E and theta N using WEBE and WNBN respectively. And the segmentation probabilities can be expressed as this formula. Because it is possible to exploit WE and BE to provide better initialization for WN and BN, we investigate the prediction of novel white matter tracks with the logits HE of existing white matter tracks given by the trained ME. For simplicity, this prediction is achieved with a logistic regression. We can get a scalar voxel-wise formula for this prediction. And we can further vectorize it for all novel white matter tracks. Then from the existing white matter tracks to the novel white matter tracks by substituting the formula of logits. We can further derive the prediction formula. Comparing these two equations, we notice that instead of being randomly initialized, theta n may be better initialized using the information in theta e. Here, W and B can be computed by minimizing the difference between the prediction and the annotation of novel white matter tracks. For convenience, this approach is referred to as ours 1. The derivation above suggests a possible way of using all information in ME. However, it is possible to have a more convenient implementation. This suggests that we can directly estimate W' and B' and use the estimated values to initialize theta n. This is equivalent to inserting a warm-up stage before the classic fine-tuning. For convenience, this approach is referred to as ours 2. Ours 2 not only is more convenient than ours 1, but also could lead to better performance for the following reasons. First, the warm-up strategy allows a more adaptive use of the information. It can find the initialization corresponding to the decomposition as well as possibly better initialization that may not be composed as ours 1. Second, the separate computation in ours 1 could accumulate the error of each computation and slightly degrade the initialization. We use the state-of-the-art TrackSeg architecture as our backbone network. TrackSeg is inspired by the UNet architecture, where the inputs are fiber orientation maps. It performs 2D processing for each orientation separately. For test scans, the results of each orientation are fused by averaging for the final 3D white matter track segmentation. Now we present the evaluation of our method. We use the DMRI scans in the HCP dataset for evaluation. The image resolution is 1.25 mm isotropic. We selected 16 and 12 tracks as the existing and novel white matter tracks respectively. The list of the novel white matter tracks is shown in the table. They were randomly selected from the bilateral white matter tracks. The existing white matter tracks corresponding to the remaining white matter tracks in TrackSeg. A segmentation model was trained for the existing white matter tracks using 65 DMRI scans. For segmenting the novel white matter tracks, we selected 4 other DMRI scans for network fine-tuning, where 3 DMRI scans were used as a training site and 1 DMRI scan was used as a validation site. For evaluation, the proposed method was applied to 30 test scans that were different from all the training and validation scans described above. We compared our method with three competing methods. The first one is baseline track set network that was trained from scratch with the annotations of novel white matter tracks. The second one is a representative convolutional registration-based method Atlas FSL. The pipeline is shown in the figure, where an atlas is created from the available annotated scans and registered to test scans for segmentation. The third one is the classic fine-tuning method based on the segmentation model for existing white matter tracks. What's more, we also computed the upper bound performance, where abundant annotations were available for the novel white matter tracks, and the segmentation network was trained from scratch using annotated scans for reference in quantitative evaluation. The proposed method was first evaluated qualitatively. Cross-sectional views of the segmentation results for representative test scans and novel white matter tracks are shown in the figure. The manual delineations are also shown for reference. It can be seen that the results of both our strategies better resemble the manual delineations than the competing methods. Next, we evaluated the proposed method quantitatively. The depth coefficient between the segmentation result and the manual delineations was used as the evaluation metric. The average depth coefficient for each tract are shown in the figure. In addition, we compared ours two with the other methods using paired cell density tests and measured the effect sizes. We can see that our method achieved higher depth coefficients than the baseline Atlas FSL and the classic fine-tuning, and the performance of our method is much closer to the upper bound than those of the competing methods. Also, ours two highly significantly outperform the baseline method Atlas FSL and classic fine-tuning with large effect sizes. The performances of ours 1 and ours 2 are quite similar, which is indicated by the close average coefficients and small effect size. Combined with the significant difference between them, these results show that ours 2 is constantly better than ours 1 with a very small margin, and this is consistent with our derivation and expectation. In addition to the experimental setting above, to investigate the impact of the number of training scans annotated for the novel white matter tracks on the segmentation accuracy, we considered two additional experimental settings. In the first case, we use one subject to train, which corresponds to a one-shot setting. In the second case, we used 5 subjects to train and 2 subjects to validate. We computed the average depth coefficient for each tract and each method under these 2 settings, and the means of the average depth coefficients are shown in the table. Under these 2 settings, our method still outperforms the competing methods. In particular, the performance of ours 2 is very close to upper bound with 5 annotated training scans, and with only 1 annotated training scan for the novel white matter tracks. The performance of either ours 1 or ours 2 is better than that of a classic fine-tuning with 5 annotated training scans. In addition to segmentation accuracy, we considered the relative volume difference between the segmented novel white matter tracks and the manual delineations as an additional evaluation metric for all the experimental cities. This metric was considered because tract volume is an important biomarker that is often used to indicate structural alterations. A smaller IVD is desired as it indicates a smaller bias in the structural analysis. From the table, we can see that either ours 1 or ours 2 has better IVD values than the competing methods, and ours 2 is significantly better than these competing methods with mostly large or medium effect sizes. The performances of ours 1 and ours 2 are still comparable, and they are much closer to the upper bound than the performances of the competing methods are. Then I will summarize our research. We have explored the transfer of knowledge learned from the segmentation of existing white matter tracts for few-shot segmentation of novel white matter tracts. Unlike classic fine-tuning, we seek to also exploit the information in the task-specific layer. The incorporation of this knowledge allows better initialization for the network that segments novel white matter tracts. Experimental results on the HCP dataset indicate the benefit of our method for the segmentation of novel white matter tracts. Finally, I'd like to thank the funding support and the data providers. Thanks for listening.